All right, so welcome back. Today we're going to be talking about file I/O in both languages. It'll take the entire time today, but this probably won't extend into the lecture for Thursday because file I/O is actually pretty easy. You've been doing file I/O the entire time that you've been working with the programming languages so far because the keyboard, the standard input, that's a file. Right? So when you are reading from the standard input, you are reading from a file. When you print to the standard output onto the screen, that's a file as well. In fact, in the Unix world, everything is a file. Traditionally, what we mean by a file, though, is that a file is a unit of stored memory, usually on disk. And I say usually because, again, a file can be a lot of different things. A file can be a directory. A file can be a program, right? So directories are files. Programs are files. Something like a socket is a file. A socket is something that you open up a socket to communicate between two computers. So this computer, at either end, they have a socket, and that socket is communicating through a much lower level in the network hierarchy. But the socket connection is a file. If you want to send something to another computer, you simply write to that socket, and then on the other end, if they want to receive that message, they read from that socket. So that socket is a file. In the Unix world, everything is a file. A file is a file, a directory is a file, etc. Right? Or buffers. Right? In fact, we're going to use buffers. In fact, that's what the standard input is. If you sit there and mash the keyboard, right, and write a bunch of things, then all of your keystrokes are recorded because they are all put into in an input buffer. They're written to a file. Only when you call, say, scanf, or in Java where you use the scanner to read from the standard input, does it start reading from that file. It's a buffer that if you mash the keyboard a million times, all that stuff is stored in there, and then it can start reading it in the order that it was received. But from our perspective, a file is usually something that is stored on the file system for persistence. Usually, files are stored long-term for persistence of data. Programs have a short lifespan. Most of the programs that you've written and run execute in a matter of microseconds, right? Or maybe a couple of seconds if they're inefficient or if they're long. But what you need to do is you need to be able to save data from one run of your program to the next. And the only way that you can do that is by persisting it to disk or some other medium so that you can save it so that it's loaded up on the next run, right? You can read or write to a file, read from or write to a file. When we say read from, this is input. This is what we mean by input. And when we write to a file, this is what we mean by output, okay? Files may be plain text or binary, right? Or they may be plain text, but not intended for human consumption. In other words, they might be a plain text file, but it's certainly not a text that it's intended that the humans read, like a book or something like that. For example, data interchange formats, EDI, right, which is electronic data interchange, right? So how do you transmit data from one computer to another? Well, at the lower level, that's networking stuff, but up here at the higher level, I have data. How do I transmit it? I need some sort of a standard so that these two programs can speak to each other. There are lots of standards out there, for example, XML. That's something that you'll do tomorrow in your lab. You'll open up a plain text file and then output an XML data formatted file. Or JSON, JavaScript object notation. It's a much lighter weight version, or lighter weight way of transmitting data that two applications can then read. Or base 64 encoding, right? The quintessential example here that I like to give is email. If you take an image and you put it in an email and you send it off, email is a purely text-based protocol. It doesn't handle binary data at all. So what happens is it takes that binary data and it changes it into text data using A through Z, capital and lowercase, That gives you 52 characters. Then 0 through 9 gives you another 10 characters. And you need 2 more. I think it's a equal sign and maybe like underscore. I forget what it is, but there are 2 other special symbols that it uses. And it takes that binary data and it transcodes it into base 64 so that it's purely text-based data. Then it gets transmitted over the network. In your email client, Gmail or something like that, it sees that it's an encoding, it decodes it, and then produces the actual binary file for you. So files can be a lot of things. They can be regular plain text files intended for human consumption, not intended for human consumption, using many different standards, right? The basic steps for processing files are, 1, you have to open the file. Right? Makes sense because you open files all the time. You double click a file and it opens it up in the proper application, right? You're going to do that in code as well. Then you process the file. Now, if you're processing it for reading or writing, then there are 2 different techniques that you use, but it's the same idea. You either read from the file or you write to the file. And then finally, 3, you need to make sure that you clean up after yourself. So if you've opened up a file, what do you need to do? Close it, or save it and close it basically if you're doing something in an application. But for us, with encoding, that means closing the file. Right? Failure to close the file could lead to undefined behavior. 99 times out of 100, the operating system will save you from yourself, but it's that 1% of the time that it won't, and goodbye data, right? Corruption of data, right? So let's go ahead and start with file I/O in C. Right? So files in C are represented by a pointer type. File, and it is all uppercase F-I-L-E star. Now, why do we use a pointer to denote a file? Think about a file that you open up. Say it has 4 lines here. A pointer will point to the first line, the first character in the first line. As you read it, say that you read the file line by line. That pointer will advance to the next line. You read the second line, that pointer will advance to the third line. Right? That's why we want a pointer, because it points to some location in the file. The file is stored somewhere in memory. And so it makes sense that this pointer is pointing to somewhere in the file because it's in memory. It's a pointer to memory somewhere. Right? To open a file, use fopen. Right? So I'm using elision here to, sometimes people just call this fopen, fclose, f-whatever, right? I like to bring them all together using elision, and it gives us a brand new word that we can pronounce, fopen, right? It takes 2 arguments. All right, it takes 2 arguments. Both of them are strings, by the way. The first one is a string that denotes the path and file name you want to open. Let me give myself some more room here. And also, remember, we are online here with questions on Piazza and YouTube. Yep, good. We got tone. The second one is the mode you want to open the file in. For example, you can use W, right? And it is a string representing the mode that you want to open up the file in. W would stand for what? Writing. In other words, output, file output. And if you use R, right, there are no 3 R's, right? Reading, writing, and arithmetic. There's an R and a W, and I admit I get them confused sometimes. But we've got an R here for reading, of course. Reading a file means file input, okay? And it is a string. You do use double quotes on these. It's a string because there are other modes that we're not going to talk about. You can do appending, you can do binary, binary plus, and a bunch of other things. So don't worry about it. Just understand that it is a string. Even though we're only passing in 1 character, it is treated as a string. Right? If successful, it returns a valid pointer. Right? If it's not successful, what do you think it returns? It returns null. It could not open that file for whatever reason. What are some of the reasons that it might not be able to open the file? What do you think a failure condition for a file would be? I want to open up the file to read it. Uh-oh, it doesn't exist, right? It may not exist, right? Opening for reading, right? Another example. There's this nice file over here in any Unix-based system called the etc password file, which we can read, right? Except that where the password used to be stored a long time ago, it's been redacted, right? The passwords are now stored in the etc shadow file. Do you think I should be able to read that file? Probably not. Why? There are passwords in there, permission denied. You don't have read permission. You might not have write permission. If I want to change somebody's password, certainly I should not be able to do that either, right? So it may not exist. You may not, your program may not have the permissions to do so, right? Especially if it's a sensitive file. So let's go ahead and take a look at an example, right? Or examples. I'm going to go over here, and let's go ahead and open up a file for reading, right? So file, right? And if you're going to read a file, it's an input file. You can call it in, you can call it input, you can call it input file. I'll just go ahead and keep it simple in, right? If you've got multiple things, then of course label them what they are. But in this case, I'm just opening it up as an example. I call fopen, and I provide it 2 arguments here. If I want to open up a file in the current working directory for input, then let's say that it's data.txt, right? And I'll read, and it's an input file, so what kind of mode do I want here? I want to read from the file, right? And that returns a valid pointer if successful. Now, take a look over here I'm right here in this code directory. If I list all the files here, do you see a data.txt file? Nope. So, if in is null, then printf unable to open the file data.txt. Right? And this is probably going to end up being true, right? Because we can't open this file because it doesn't exist. gcc a.out, unable to open the file because it does not exist. Right? What if I did it instead for output instead? What does that look like? Instead of reading, I want writing. Right? Am I going to get the same error message here? No. In fact, what do you see happened over here? It created it. So if you open up a file for writing, it'll create the file for you. Excellent. Now, be careful. What if there was stuff in there already? Hello, world. How are you? Really valuable data here. Right. I'll save that. Right. There. So well, let me go ahead and more data. Right. Really valuable data. What if I run this program again? Goodbye, really valuable data. Right. Why? Because it opened it up. I didn't write anything. And eventually it closed it and cleaned up for me. And all that valuable data is now gone. It was not valuable data. Yeah?
How do you make small edits to something?
If you're, that's going to, we're not going to get into it that deeply, but the question was, how do you make edits to a file? Like, you want to open it up and you want to go to line 20 and you want to replace line 20 with this, but you don't want to disturb lines 1 through 19 or anything after it. You have to open it up for appending or changing, and then you have to, or you have to advance the file pointer and then to the right spot and then edit it and then make sure that you preserve everything else. We're not going to get into it that deep. We're just going to read and write. But you would have to do, you'd have to do some additional work. Yes. Right. So that's opening for reading, writing. Of course, if I ended up opening, say, something that is at a relative location, for example, the etc password file, do you think I should be able to change that file? Now, I showed you before that the password file, I can read it because there are no passwords in there. They've been redacted. But do you think I should be able to write it? Hopefully not. Unable to open that file for writing because that file does not belong to me. But I was able to demonstrate that you can use an absolute path, right? That starting at the file root system in the etc directory, which is just a different pronunciation of etc., right? There is this file called password. It's not password.txt, there is a password wd file, right? And I can also do, say, relative paths. So if I go up one directory and then down into, I don't know, archive, then setup.sh. And I'm not going to open this up for writing because I don't want to clobber my file. There's a term for you, clobber, K-L-O-B-B-E-R, right? At clobbering time, somebody hits something, right? You clobber it. That's what, when you do that to a file, you're overwriting the file accidentally, you clobber the file. And you don't generally want to do that, right? If I want to open this up for reading, I can do that too. Because that, of course, that file belongs to me, right? And it's perfectly happy with that. So you can provide relative paths, you can provide absolute paths, you can provide just open this up for reading in the current working directory, okay? I'll make sure that you have all of this in your notes. In fact, let me go ahead and cut and paste this. All right. So open up a data file in the current working directory. It's just a file name for reading. Right? You can use relative paths. You can go up 2 levels, then down into the My Data folder, and then input.txt. You can use absolute paths, like opening up from the root file system. That's what this first slash is. In the etc directory, open up this one. And of course, it can fail. If you try to open up the shadow file for reading, that does contain passwords. No way, you can't do that. Right? Okay? So what about closing a file? Closing a file. Right? To close a file, simply use close. Right? Pretty simple. If you open it up with fopen, fopen, then to close it, you use close. You pass in the file pointer of the file you want to close. Right? Failure to close a file may result in corrupted data or incomplete data, or pretty much anything, right? It will 9 times out of 10, it'll take care of it for you, but at the end of the day, make sure that you're doing it you're doing it, because it's kind of like memory. When you use malloc to create a chunk of memory, to allocate a chunk of memory, once you're done using it, make sure that you are freeing it up properly, because if you don't, then it's either a memory leak or at worst it's a memory leak, I guess, if you don't free it up. Right? So it's just close and then pass in the file pointer. This is the file pointer I was using up here as the example. Right? So I kind of went to step 1 and then step 3. We kind of skipped that step 2 because I wanted to get the simple stuff out of the way first. So what about file output? That's the easier one. Right? There are many ways to do file output. Let's keep it simple. Stupid, right? Let's keep it simple, stupid, right? I'm only going to look at one way of doing it, right? You can use fprintf to do file output. So you are familiar with printf already. That outputs to the standard output. Guess what? The standard output is a file. So if you want to provide an alternative file to output to, all you need to use is fprintf. The F standing for file, right? It's the exact same behavior. It has the exact same behavior and formatting placeholders as printf, but a new first argument, the file you want to print to, right? So let's take a look at a really quick, nice example here. I'm going to go ahead and change this to an output file, out is what I want, and it'll be for writing, and I don't want setup to, I'll just go with data.txt here, right? Get rid of that. Of course, you can do error checking here, but I'm going to keep it simple, and let's just start writing to it. If I did printf, hello, how are you, right? That's going to print to the standard output, right? How do I change that so that it prints to the file instead? fprintf, and I provide the file name as the first argument. If you have variables that you want to print, x is equal to 42, double pi is equal to 3.14159, everything that you've learned about printf can be used here. So let's make one more char, name, Chris, there we go. fprintf, let's put in a bunch of end-line characters so that we can see that it'll preserve any formatting that you do. fprintf, hello, %s for Chris, pi is %.2f, and x is %d, end the line. So I can provide, say, my name, pi, and x all as arguments. What do I need to do at the end? To close it, right? Close the output file. Oh, and by the way, what do I need to do here? Sorry, I forgot those. There you go. GCC this, and let's run it. Of course, it didn't echo anything because I didn't print anything to the standard output. But if I open up this data file, yeah, reload it. Reload, there you go. You see what happened. Hello, how are you? End the line. 3 blank lines. Then hello, Chris. Pi is 3.14 because I only went out to 2 decimal places. And x is 42. So cut, paste all of your brain knowledge for printf, and you can do file output simply using fprintf. Okay? That's why this is only going to take one day, right? Because you have been doing all this stuff before. Yeah, go ahead.
Is this how you do your notes for class?
No, my notes for class are Markdown. So I'm using Atom.io over here, right? And then this is the Markdown preview of this. And so when I upload them to GitHub, of course, you'll use the GitHub Markdown preview. I don't have any here. Oh, wow, everything's slow today. But say the notes from, I don't know, from error handling, right? It'll look like a nicely formatted, you know, there's code, I go into code mode, et cetera, right? All right, so there's file output. And again, if you open an existing file and start writing to it, it overwrites the data, right? It clobbers the file. Right? I think it's with a K. Maybe it's with a C, I'm not sure. No, it is with a K? Yes, no? I don't know, what does the thing say? Clobberin time, the thing. Oh, it is a C, okay. It's clobberin time, right? The thing says it's clobberin time, right? So it's with a C, there we go. It clobbers the file, right? It overwrites it. So you have to be careful. If you want to do something fancy like opening it up and only changing one part of it, then you're going to have to, you know, advance the file pointer to exactly where you want, opening it up in a different mode, like a pending mode or something like that. Right? There is no undo. There is no undelete. Right? This is not a full application like a Word file where if you screw up and you accidentally delete a paragraph, you can just go Control-Z or undo. It doesn't work like that, right? And this is a full file system with great power comes great responsibility. So you have to make sure that you know what you're doing. Yeah, you got to be careful. And of course, you can write a more complex program so that you do have an undo of some sort. You can back up the file before you start processing it in memory or on the physical disk or something like that. There are a lot of ways to do file input. Right? Most are dangerous. Right? Most are also complicated. So what I'm going to do is, again, keep it simple. I'm going to show you 2 ways of doing it in C. You can use fgetC or fgetS. So fget, well, that's going to be file, and then get, of course, we're doing input, so we're reading from the file, get it from the file. C and S, what do you think the difference and distinction there is? Character versus S stands for strings, right? So F get C gets and returns a single character from the file at a time, advancing the final pointer to the next character automatically. You don't have to worry about that. If it's got A, B, C, D, you read A, it advances it to B. You read B, it advances it to C. It takes care of it for you. End-line characters do count as characters. Null characters, if they are in a file, count as characters. You don't want to do that though, because plain text, you don't use null pointer character, or null terminating characters in text, right? In data you do, of course, but not in plain text files. So let's go ahead and take a look at an example here. Now that I've got this data over here, let's actually add some stuff here. And usually what I do is I do Lorem Ipsum stuff. So here's a good life pro tip. If you ever just need random text or data to work with, just pull some Lorem Ipsum text. Lorem Ipsum text is used by typesetters, by graphic designers all the time. It's just simply dummy text that you use as a placeholder, right? Where does it come from? You can read about the history here. Where can I get some? Here's an example. I think it's just random quotes from something, and it's not intended as English, of course, because it's Latin. But of course, you can play around with it and have fun. Yesterday, I did Lorem Ipsum from Star Wars. It was just a bunch of random Star Wars texts. There we go. Generate that. And just random stuff. Or you can actually have full quotes if you want to have even more fun, right? This one here. Okay. It's fine. There we go. We don't serve your kind here. What? Droids? They'll have to wait outside, blah, 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 blah. So here's just random text, random quotes from Star Wars movies. And if you just need data, then sure, go ahead and put that in there. Generally, I like to use English stuff more than Latin, because I can read it and I know, okay, yeah, that looks correct. Luke, yes, but Lorem Ipsum, I don't know if that's correct. I'm going to have to go back to my text to find out, right? So now that we actually have some data to work with here, let's actually go ahead and process it. It is going to be an input file. We're going to read from that same file that I just pasted a bunch of stuff into, but we're going to open it up for reading. Okay, let's open it up for reading and just read maybe the first 5 characters. So char C, C is equal to F get C of, oops, not int, but in, there we go. And then let's print it back out, printf, %C to print the first character. Right? And let's actually go ahead and put a space in there so that you know that these are actually characters. We can do it again. The first character, second, third, fourth, fifth. Right? And let's see that it works. Oops. Not out. Where's out? Oh, here, in. There we go. All right. So we should, what was in here? We don't serve their kind here, right? So we should see, we do, and then this is the space character that was in the file. Spaces are treated as characters. They're not skipped. We do not serve their kind of, blah, blah, blah. Right? Well, that's all fine if I want to read character by character by character and I know how many characters there are going to be. But of course, this is just going to be cut, paste, cut, paste, cut, paste. How can I avoid that? If I want to read every single character, process it character by character until the end of the file. What other thing should I do? Probably what? A while loop. While not at the end of the file, right? Then I'll print it out and I will get the next character. Right? Why did I immediately put a while loop up front? Why not a for loop? Do I know how many characters are in the file to begin with? No. So a priori, I don't know how many iterations this is going to go until I reach the end of the file. How do I know that I'm at the end of the file? There is this special character that is not in the ASCII text character set. It is just a special flag character called EOF. While the character is not equal to EOF, then continue. What do you think EOF stands for? End of file, exactly. Right? It is a macro. It is a value that is defined. In fact, all the stuff that we've been using is in the standard input-output library, so you don't have to bring anything new in. But once you reach the end of the file, then it returns EOF. Right? So it reads one character at a time. When the end of the file is reached, it returns a special flag value EOF, right, which stands for end of file. This is not a character that you can print. This is not a character that is in the ASCII text system. It is entirely operating system, or file system, I should say, dependent. What sequence of bytes is used to denote the end of the file? That's up to the operating system. And for Windows, it could be different. For SUSE Linux, it could be different. For Ubuntu Linux, it could be different. Probably not, but it's built into the standard input-output library to use this symbol. Right? So while you've not reached the end of the file, continue, continue, continue. Let's see this one in action. And I won't print that. Yeah, I'll go ahead and print out like double spacing around everything. And you can see there. It looks quite different than the input, but you can see that it did everything. Did he take those two new droids with him, blah, 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 and then at the very end, hit the accelerator, period, end of file, and that's actually what's at the end of the file. Right? There, hit the accelerator, period. That's the end of the file right there. Right? Cool. The second way of doing file input is a little bit more efficient. This is if you want to do it character by character. The problem with that is that file I/O, in fact, all input-output, is quite expensive. That's going to be your bottleneck in any computing system. So generally what you want to do is you want to set up a buffer, meaning that you don't read every single character from it. You do I/O once. You read a bunch of characters from it. Or if you're writing to a file, you don't write every single byte to the file because writing to disk is very, very expensive. Instead, you fill up a buffer, and then you flush that buffer to the output. Flushing just means that, okay, I'm going to go ahead and write like 4 kilobytes all at once because this is expensive. I'll do it all at once so that I'm not paying that expense over and over for each character. I'm paying it once for this chunk of data. Right? Now, on the input side, that means using fgetS. Yeah?
Why would writing to the thing over and over again for each individual character be more expensive than like writing the same amount of characters, I suppose?
Well, I mean, even writing one byte, I mean, think of it in terms, it's not exactly like this, but think of it in terms of a hard drive versus, memory. Like main memory RAM, that's way faster. But actually writing it to the hard drive, right, that's mechanical, that's way slower. So if you write one byte and then probably context switches out and other programs take over, then you come back and you write 1 byte. Whereas if you just wrote the entire, like 4K or something like that, it's going to cost you just as much as writing 1 byte because the needle still has to move, basically. Right?
You're just telling it to do it all at once?
Yeah, do it all at once and pay for the I/O, but only do it once instead of 1,000 times. All right, let's see.
So it just seems like less work, I guess.
Oh, it's definitely less work because you can see, a program that prints stuff out to the output is going to take way longer than a program that just does everything in memory and doesn't print anything because it doesn't do any I/O at all. In fact, we've seen this that I don't know, was there any perceptible? All right, there's a little bit perceptive, like it wasn't immediate because it was doing input and output. But if I had not, printed anything and just read in the file, immediate, way faster. Right? Now, that was not that perceptible, but if I double this up and make this, I don't know, large, I don't even need to recompile it here. Right? Immediate, but printing it out, Okay, that was immediate too. I'd have to make it really, really large to make it human, noticeable by a human, right? But that's the idea, okay? You can use fgetS to read up to an entire line of text from a file at once, okay? So what does that function look like? I'm going to go ahead and go to the man pages here and fgetS, right? There it is. It takes 3 arguments and returns something that is not a character. So here is the signature. There we go. So let's talk about each one of these things. The first argument, S, is the input of the string. You want the result from the file to be stored into, right? Usually we refer to this as a buffer. It is a buffer. Right? In fact, that's what I'll name my variable when I do this, buffer, right? Because we're storing in one line at a time. The size is a parameter that says that fgetS will read at most size minus 1 bytes from the file and place the results into S. Why minus 1? Null terminating character. It takes care of it for you. Minus 1 to accommodate the null terminator, which it takes care of for you. Right? Actually, it reads up. I said that it reads up to size minus 1 bytes because it stops when it sees that first end line character. It stops when it sees the first end line character. Right? And the end line character is not the same thing as the null terminating character. The end line character is /n. Or if you're on a Windows system, it's /n/r. Don't worry about that though, because if you're on CS50 or if you're on CSE, you're not on a Windows system. Yeah?
Is that because like it's the end of the line anyways?
Exactly.
It doesn't matter what it is.
Yep, it reads one line at a time. That's the behavior. Up to one line at a time, because if you only read 100 bytes, but that line is 300 bytes, it will only read that first 100 bytes and then stops, minus 1, puts in the null terminating character for you, and then hands that over. So when we create the buffer, I'll end up making it large enough to hold anything that we need. All right. Finally, the last argument is the file you are reading from, right? The file pointer. Right. It return upon success, it returns a valid pointer to the resulting string. Right? In other words, S again. Upon failure or on reaching the end of the file, it returns what? What's the only thing that it can return if its a return type is a char star to indicate I'm done? Null, exactly. So we can write another loop here to read the entire file line by line. Right? And you know what? Let me go ahead and reverse what I did here so that we only have these first 3 lines. Okay. Note, however, how many lines do we actually have here, though? A line full of text, a blank line that it will read, right? Another line full of text, another blank line. So we have at least 5 lines here. Let's see what it looks like. So I'll still open it up for reading, but instead of reading a single character at a time, I'm going to read an entire line at a time. Now, to be safe here, let me go ahead and look at the longest line, and there are 672 characters in that line. So I'll simply make my buffer, my string buffer, large enough to hold the contents. Now, what if I went back and made a line that was 2,000 characters long? Right? Now it's not going to reach the end of that line. In other words, it'll read the first 1,000 minus 1, so 999 bytes, and then the next time that I call fgetS, it'll give me the rest of that line. So you have to be careful, right? How do you know the difference between whether or not you've read to the end of the line or you're still reading the same line? It takes a little bit additional coding. 1,000 is good for us now, though. Okay. Let's go ahead and create a char star s, right? And I will call fgetS. What are the arguments? The string that you want to read into, so in this case, buffer. Right? The size, well, it's 1,000. Don't worry about minusing 1. I don't have to put 999 because it automatically does the math for me. So as long as this number matches the size of your buffer, you're good to go. And then the input file stream that you want to read from. Right? I can reformulate this while loop to check for null instead. While s is not null, in other words, while you've not reached the end of the file yet, go ahead and print it out, but it's no longer a character, it's an entire string. Right? And it's stored in the buffer. And then set yourself up for the next iteration by simply doing the exact same thing that you did before. Right? All right, let's see how this works. There we go. And of course, it's line breaking simply here. It's not actually line breaking, it's just fitting it in because of this output. There's the actual first line. There's the second line that's blank. There's the second line that has actual text, third line, and then finally that trailing end line was not read as a line. Yeah?
Does it do you didn't put like the \n?
I didn't put it here because it's already there. Right? Over here, there was already an end line character at the end of this line. Right? It's preserved. Right? So there's another note. fgetS will preserve the end line character if it sees it. Right? So that's how you can distinguish. Am I at the end of the line or am I reading? No, because the end line character is not in the buffer. So I must, if I call it again, I must be continuing to read the same line. And that's how you can distinguish. If you don't want that, if you don't want the end line character, you can trim or chomp it out. There's another term like clobbering, chomp. Chomp just simply means to remove leading and or trailing white space. All right? Chomp it out. I think it's from Perl. Yeah.
Will you be able to see any line characters?
I mean, not like an escape like /n or anything like that, but you can see it that it went to the next line, right? That's why we got a blank line. That blank line went to the next line. So, I mean, if you want a substitute character for an end line character, you'll have to explicitly do something.
But how do you know that there's an end line character in the text file?
Good question. So, I can check. If the last character in buffer is the end line character, then I can do something with it, like get rid of it, right? So how do I check that the last character in the buffer is an end line character? Well, I can use equals /n, that's the end line character. How do I get to the last character though? Buffer sub, where's the last character? If it's 5, then it's at 0, 1, 2, 3, 4. So how do I know that it's 5? str, length of the buffer, and then of course -1. If the last character is an end line character, then you want to chomp it out? Let's go ahead and chomp it out. Set it equal to what to get rid of it? The null terminating character. Right? That's how you can get rid of it. So chomp out the last end line if it exists. Right? I'll make sure that you've got this in your notes as well. But again, it is preserved. If you want to get rid of it, you can go ahead and chomp it out. Right? Or you can, if there's like tabs and spaces, trailing spaces, then you can write your own function to trim all that stuff entirely. Or if it's a proceeding or something like that. Or if you've got white space characters all over the place and you just want to remove them all, you're doing that in homework 5. Right?
I was just asking, like, because when we do printf, like, we can see the.
Not with printf. There's no. They're white space characters, so it's going to print white space. Just like all the lower end ASCII text characters, they're non-printable characters. There's no way to print them unless you escape them somehow and print the ASCII text values instead of the actual ASCII text. All right, so questions so far on this? Otherwise, let's go ahead and switch modes and talk about Java. All right? In Java, it's even easier. Java defines a class called file. It is capital F, lowercase ILE, right? And input files, output files, it doesn't matter, they're all the same, right? So you can create a file, Java. You can create a file by saying file F is equal to new file, right? In the current working directory, file.txt, there's no mode because a file is a file. It's not a file that you've opened it up for reading or writing yet, right? That's not like C. Or file F is equal to new file in an absolute path to file.txt, right? Or you can have a relative path, new file, say up 2 levels, and then down into archive, down into file.txt. Right? There are lots of ways of doing file input. Again, I'm going to keep it simple. File input, lots of ways, but keeping it simple. Use a scanner that you're already familiar with. Right? Remember, we used a scanner to scan the system.in. What do you think system.in is? It's a file. It's actually a file stream. But it's the same principle. Right? So let's go ahead and go over here to Eclipse in demo here. And I've got some data here. These are from old assignments here. Oh, here. I've got a Pokemon CSV file. I wonder what's in that. Cancel. Quit out of numbers here. Open with, here's a trick in an Eclipse. If you don't want to open it up in some external program, you can just open with, and then just make sure that you select text editor, and it'll open it up right in Eclipse here. So here's a bunch of CSV data based on Pokemon that I think I did a final exam on once. So there's their ID, there's their name, and there's their type, all separated by commas. Let's go ahead and open up that file for processing. Right? New, I think I've got a demo here already, right? Yeah. Okay. Let's get rid of all this stuff. So I want to create that file first of all. File, F is equal to new file. And where is it? It was in what, the data folder, was it? Data and then Pokemon.csv. So data, Pokemon.csv. I've never played Pokemon before myself. Are you guys past the generation that did? No? Okay, you are still a generation that played Pokemon? Okay, all right. I was a generation ahead, so we never got into it. Sorry.
You never caught any of them.
Say what?
You never caught any of them.
No. I tried the mobile app with my kids, but then we quickly realized that once you run out of the Pokeballs that you have to pay an exorbitant amount of money, and I'm like, no, never mind. Forget this. It was fun while it lasted, but no. So I want to open this up for, say, reading, right? What I can do is I can create a new scanner. S is equal to new scanner based on that file, okay? Now, everything that you learned about scanner to read from the standard input, if you want to read an integer, go ahead, read an integer, s.nextInt, right? Not has nextInt, but nextInt. Int x is equal to, we'll take care of this here in a second, right? If you want to read in the next line, then string line is equal to s.nextLine. Right? If you want to read in the next string, strings are by default, they're delimited by white space, so if it's hello world, how are you, then I would have to call it once, twice, thrice, 4 times to get each one of those strings, right? So why is it griping here? Unhandled exception, file not found exception. If a file doesn't exist in Java, it doesn't return null. It doesn't crash. It throws this file not found exception. Now it's a checked exception, so I have to surround it with a try catch. There. New scanner, and of course, now everything should be done in this try here. Right? And let's print these out. Actually, there is no X in there, right? So I'll just go ahead and get the entire line, system.out.println line. Right? And then we could go ahead and do that again. Not the same one, but let's go ahead and run this and see what happens. There's that first line, Bulbasaur. There's that second line, Ivysaur. Right? There we go. Does anybody have these memorized, maybe? No? Okay. How many are there? 151, apparently. And the last one is Mew Psychic. There we go. All right. So how would I read every single one? I would want to go into a while loop, right? While s dot has next line, or if you're reading it, character by character or something like that, then has the next integer, or has the next double, or has the next string, or whatever, right? While it still has another line, let's go ahead and read it and output it. And then, of course, make sure you format correctly. This will break out once you are done, right? Once it's done with the file, excuse me. So there's the last one, Mew Psychic 151. Right? It does not preserve the end-line character because I am printing the end-line character manually. So that is another difference. If I'm not printing the end-line character, then you can see that that end-line character is not preserved. Tokens are not preserved with scanners. Okay? There we go. When I'm done with it, what should I do with the scanner? I opened it, right? If I open it, what should I do with it? S.close. That basically closes the underlying file as well. Okay? If you don't do that, then again, 99 times out of 100, you'll be fine. It's that 1% of the time that you're not fine that you'll regret not doing this. Right? In fact, there's a more modern way of doing this. Scanner S is equal to new scanner F. There we go. This is a try with resources, and it automatically closes it for you. You see that syntax there? I don't want new scanner. There we go. The syntax is try opening this resource. Don't worry about it. I'll take care of closing it for you. Right? Now it closes it for you. Right? Try with resources. It closes it for you. It's not new. It's like Java 8 or something like that. So it's a good 10 years now that it's been in there. Right? But there's an example, and I'll make sure that it's over here in the notes. What were some of those observations we made? You can use any number of next methods to get tokens out of the file, right? By default, the white space is used as a delimiter, right? And the delimiters are not preserved in the result. Right? So all those end-line characters, they got chomped out automatically. Right? You can use s.hasNext line or hasNext whatever, right, to test if you are at the end of a file. Right? And so you can use this kind of loop up here. A try with resources construct will automatically close the file for you. Right? Cool. You just have to make sure that you're using a modern Java. If you're stuck on, like, say, Java 6 or something like that, first of all, my condolences, but second, good luck. What about file output in Java? Right. Again, many ways, but keep it simple. Right? We're going to use print writer. And I forget the details, but of course you can read the book. I put the details in there with a couple of alternatives. I think I suggest print writer because it is a buffered output. I think there's a default buffer of like 4K, so it's going to be way more efficient. But let's go ahead and take a look at an example here. I want to make sure that I'm not clobbering any files here. So let's go ahead and open up a file called Pokemon output.txt, right? And we'll go ahead and open this up, not for a scanner. Let's go ahead and open it up for with a print writer. I'm just going to get rid of all this, and then we'll start from scratch here. A print writer, PW, based on a file, and I just need to import this, I believe. Yep, it's in the java.io. So java.io file, java.io file not found exception, print writer, all this stuff is in java.io. Right? And it's going to complain because, of course, add a try catch here, file not found. If you don't have permission to open this file up and start writing to it, then of course it's going to fail. Right? So once again, I could, put this into a try with resources. Print writer is equal to this. There we go. And it'll close it for me. Yay. Now I don't have to go pw.close. Right? Once I've got it open, the reason that I suggested a print writer is because it is exactly like system.out. System.out.print and pw.print. My favorite Pokemon is ... Well, that doesn't print a inline character because printf does, or println does, right? Is ... Ryan Reynolds. Right. There we go. pw.printf can also be used. Here is a number, right? And int x is equal to 42. %d and the line. There we go. And then x. Right. I don't have to worry about closing it because, of course, it closes it for me. When I run this, no news is good news because I'm not actually printing anything. But you'll see over here, wait, I don't see a file. In fact, somebody asked about this on Piazza. Eclipse is notorious for not syncing with the file system. So if you ever have this issue, go ahead and right-click, refresh, and you see that Pokemon output.txt is now a file over there. It's a file that I can actually open. There we go. My favorite Pokemon is Ryan Reynolds. Here's a number 42. Right? So there's file output. And again, using that try with resources means you don't have to close it yourself. And the reason that I suggest that you use a print writer is because a print writer allows you to use printf or println or printf. Basically everything that you've used up to this point with system.out. Right? So, easy in a nutshell. Any questions so far? No? We've only focused on text data. Now, some of it has been CSV data, which you can combine all your knowledge from strtoke and string split to process tokenized data like you would potentially with this Pokemon CSV data, right? You would read in a line and then chop up that line into a tokens and then create a Pokemon or whatever you want, whatever you're wanting to do with it, right? You want its type. I think that the idea here was that if one type fights another, they've got a multiplier for damage, right? So if a fire, attacks water, it's not going to be effective at all, or less effective, I don't know. But if water attacks fire, then it's way more effective, right? And so the assignment that I gave was, given a Pokemon name, you had to look up its type, and then the other type, and then in another file over here, Pokemon types. Let's see, open this up in the text editor. If a rock attacks a poison, its multiplier is 1. Or, I don't know, is there something more interesting? If a bug attacks a normal, then it's 1. Here. If a bug attacks a psychic, for some reason, bugs are really effective against psychics. Why? Tell me. No? Okay. Nobody knows. That's just the way it is. All right. Okay. So all bugs are venomous, I guess? All right. I'll buy that, sure. But we've only focused on text data, and CSV data, of course, falls under that. There is also a whole category of binary files, binary file I/O, right? So, with only 15 minutes left here, here's my sage advice. Bring in a library, right? Don't do that yourself, right? If there's binary data out there, then it has some sort of a format. And if you have a format, then somebody else probably wrote a library to do it for you. For example, in, I think, was it labs 5 and 6, when you were working with the image manipulation stuff in C, we brought in a library, an STB library, to do all the file and manipulations for us, because we didn't want to write code to support JPEG and GIFs and PNGs and whatever else, TIFFs and whatever else other image data is out there, right? But image data does have a prescribed protocol for what it looks like. For example, if you look up a GIF on Wikipedia, right, it tells you what the data looks like in a GIF file. Here we go. It starts with this magic number that indicates I am a GIF. It is GIF 89A format, right? So that's 89 is the year that it was created. And every GIF file will begin with this. Then followed by a table of colors, followed by all the pixels. It doesn't store the pixels directly. It says, this is a pixel that is of type 43. And then you go back to that metadata table and you say 43, okay, well that has this RGB value. Because GIFs are limited to 256 colors. If you allow arbitrary number of colors, then of course it blows up in size, and you've got PNGs, which are much, much larger. And then you can also have JPEGs, which are a completely different file format. They use complex mathematics, Fourier transforms, or whatever, in order to approximate a group of pixels so that you can have compression. And you can have smaller files, but of course, lossier images, right? More pixelated. Because it doesn't actually store all the pixels, it stores a representation of the pixels in a much smaller amount. All of that stuff, big, huge headache. Bring in a library to do it, right? In fact, we can see, what I will show you though, is that, let's open up that foo file, foo.gif, right? Remember, it's just this, this flower, this sunflower image here, really, really pixelated, right? Why? Because, well, it's a GIF format, right? It only allows 256 colors. So if you've got a gradient of 2 colors, then you have to choose one or the other, right? Yeah. All right. Let's see. Sorry for not answering that online, but we did. Somebody else asked that in class. All right. So what I want to do is I want to open up that GIF and I want to look and see what's inside of it, right? Let's actually not open up a line because there may not be any endline characters. It's not a text file, right? So let's just go ahead and get the first few characters, right? Char C. C is equal to forget C in N, and then printf %C, and I won't delimit it at all, right? Let's do this 1, 2, 3, 4, 5, 6, 7 times, right? Oh, am I opening up the foo.gif? Yep, okay. All right, clear. All right, what do you think that the first few characters are going to be? GIF 89A. What's that stuff right there? That's my last one. Why did it print garbage? Because it's binary data after that, right? It's not text data anymore, right? So it is a huge headache to do stuff like this. Don't worry about it. But I do want to show you a demonstration here that you'll see in your lab tomorrow of why binary data is good, right? So output.bin for writing. Right? Let me just go ahead and create an array here, an integer array here, numbers, right? And I'll put in 4 numbers here, 2, 3, 5, and 7, right? And how many numbers are in there? There are just 4 numbers, right? You can do binary output in both languages. You can do binary input in both languages. Let me show you how to do that really quick in C here. So what I'm going to do is I've opened this up for binary output. That's just a file name. That doesn't get me binary output there. To get binary output, you can use fwrite. For binary input, what do you think you would use? What's the opposite of write? Read, right? So for write, it takes 4 arguments. It takes the thing that you want to write, and I want to write this entire array. The size of each thing in the array that you want to write, size of int, that's an integer array. Right? The number of things in that array that you actually want to write, 4 in this case, or n in general, right? And then the output file that you actually want to write to, and then close it up. Right? Let's take a look at, we'll see what this does. Oops, not in, out, there we go. Numbers, there we go. And let's just take a look at fwrite really quick. I think I got them right, but I'm not sure. Size, and then, yep, I'm right. There we go. No news is good news, but you'll see over here, hey, there's an output.bin file. If I tried to open that up, what would it do? It's binary. It's not going to show me, right? Oh. Sorry, quick key. Control W, it generally closes tabs, but because I'm in the I'm in a browser, it's going to close my browser tab instead. Sorry, but thankfully it came back really quick. All right. If I ask what type of file that is, what is it going to say? It's just data. Right? I don't know. It's data. Right? If I asked what type of file that foo.gif is, it's going to say it's a GIF. Why? Because of that magic number at the beginning of the file. It reads that magic number and says, oh, this must be a GIF file, right? I'm not an image, the file utility here, it says I'm not an image expert, so I'm not going to be able to display this file, but I can tell you it's probably a GIF file based on the magic number at the beginning of the file, right? Let's go ahead and take a look at the size of it. Output bin, right? 20. Right? Why is it 20? And yeah, why is it 20? Oh, sorry, no, that's October 20th. Today is the 20th. Duh. Here, it's 16 bytes. All right? I was wondering, why is it 20? Why 16 bytes? Where would I get 16 bytes? 1, 2, 3, 4 integers. How many bytes per integer? 4, thus 16 bytes. Storing it as just pure binary data is way faster, can be way more compact than storing it as plain text. To demonstrate that, let me go ahead and show you 1.47 billion, 2.147 billion, 123, 123. There we go. There. If I run this, of course, the size does not change. It's still 16 bytes. But if I were to print these out as characters, what would it look like? txt will write this, and instead of using for write, I'll go ahead and for int I equals 0, I is less than n, I plus plus. We're going to have to say printf %d, end the line because if I just have a string of numbers, I don't know what the delimiter is. But if it's binary, I know that the delimiter is 4 bytes, 4 bytes, 4 bytes, 4 bytes. I don't need an extra delimiter here at all. So it's way more compact to use binary. And we'll see exactly how much more compact here it is. Sorry, fprintf and out. And then we'll print numbers sub I. GCC. And there's the new file, output.txt, and you see that it's all plain text. Yeah, a human can read it now, but it is way larger. And if you had millions and millions and millions of numbers, now you're talking about files that are megabytes larger just to store them in plain text. Right? That's not what you want to do. Right? Binary is way more efficient to store. It's way more efficient to load it up and to persist it to a file, because you're just writing pure data. You don't have to load it up from the file, convert this string into an integer, into 4 bytes, and then work with it. Right? It's just going to be way easier to use binary. But, again, at the end of the day, bring in a library to do it. right? Unless you're doing some custom weird binary, you created a brand new image format, right? Good for you, and good luck doing that. All right, any questions? Is there a way that we can replace words in a file, like board replacing board? Again, not easily. Yes, there's plenty of ways, but you would have to search through generally what I would do is I would load up the entire file into memory, and then do your string manipulation in memory, and then dump the file back to the original, or to a different file, like here's the original file, and then here's the changed file if you're trying to do something like that. But yes, there are ways of doing it. Opening it up, advancing the file pointer. You can actually reverse the file pointer too, if you want to go back and forth in the file. I think it's called F rewind. Why would it be called rewind, I wonder? Anybody know? Man, rewind. Rewind. Well, storage was, exactly. Magnetic tape. In fact, to this day, magnetic tape is still going to be the cheapest medium of storage. You cannot get cheaper than magnetic tape for the amount that you can store in magnetic tape. Nobody uses it, of course, because it's extremely slow and inefficient. But on a per megabyte cost, there's no beating it at all. In fact, I'm sure that at least up till a couple of years ago, CSV backups were still stored on magnetic tape because it was so cheap. And it still is so cheap, but it's so inefficient. Literally, if I wanted something, a backup, I had to talk to the sysadmins, and they had to go back to their house to get the proper tape, load up the proper tape, and then find the proper file, and then give me the proper file. No, that's not happening. I don't think that they do magnetic tape anymore. Right? But there is is it Ferind? Oh, man, F wind? Nope. What is it called? It's something wind. So C F rewind. It's just rewind. There we go. Rewind. Why? Because it's magnetic tape. You rewind it back and forth, right? And you can still do that. Yeah. I'm sure somebody does, or at the very least, there are still plenty of old backups. When we had our first kid, now 10, 11 years ago, they had an EKG when we were going in to give birth. They had an EKG readout, and I said, "Oh, that's cool. Could I have that as a memento?" And she said, "Nope. This is going into a salt mine for storage for 20 years for legal purposes." So literally, stuff like that is still stored for legal purposes. Your own personal tax returns, when you start doing your own finances, the rule of thumb there is to save tax returns for the last 7 years, because you are legally liable for any errors in the last 7 years. After 7 years, then it becomes, statute of limitations or whatever. You don't have to keep those records anymore. But of course, if you still have, paper records, then what are you doing? At the very least, have electronic records that you scan this stuff, and then, I've got like 3 hard drives that I carry around and 4 more at home of backup stuff. And the backup hard drives are super cheap. I think I've got a solid state hard drive that's 1 terabyte. I got it for $80. Is that about right? And that was a couple of years ago, so it might be even cheaper now. But byte for byte, magnetic tape is still cheaper. It's probably not cheaper to maintain anymore, I'm sure, but it's certainly cheaper to buy, if you can still buy it. I don't know. That's a good question too, newegg.com. Can you buy magnetic tape? Magnetic tape storage. Maybe not a consumer product anymore. No. So, buy magnetic tape storage. Real, maybe. Okay, I'm just getting magnetic tape here now. You're going to have to look that up yourself to see if you can even buy it anymore. It's kind of like old school film. I think only one company makes actual film anymore, right? Kodak, I think, is getting out of the business. It's all digital now. All right, so reminder, all right, so we'll continue next time. Again, a couple, remember that I'm broadcasting from home on Thursday. I will send out a reminder announcement on Piazza though, okay?